If f is differentiable at a number, then it's continuous there. Now notice it doesn't say if it's continuous there, then it's differentiable. That's not true. It has to be continuous to be differentiable, but just because it is continuous at a number doesn't mean it's differentiable there. So let's look at some examples. So I have this piecewise function, and here's the definition of this function. So we want to find out where it's differentiable. So since it has that break, it's continuous. It's not, the graph doesn't break, but since the two pieces of the piecewise function are relative to 0, our radar needs to be up that weird things are happening around there. So this is continuous, and the domain is all real numbers. But now we're going to find the derivative and see what that function looks like. So first we're going to find the limit definition. We'll find that limit for x greater than 0. So we'll be using this part of the function. So when we use the difference quotient and we multiply by the conjugate over the conjugate, we get 1 over 2 times the square root of x. So right away we know that that's not defined at x equals 0. So this is telling me that it's not differentiable at x equals 0 right now. But just for fun, I'm also going to look at the limit for x less than 0. So this part, the difference quotient again, and I wanted to point this out because it's easy to make the mistake of plugging in here minus x plus h. But remember, you're evaluating the function of the quantity x plus h. So that means that this should be minus quantity x plus h. So if you go through the algebraic manipulation here, you get minus 1 over 2 times the square root of minus x. So you've got two different functions, and neither one of them are, one for one side and one for the other. Neither one of them are defined at 0. So this function is not differentiable at x equals 0. So this blue graph is actually the graph of this function's derivative, and you can see that it's not differentiable there. So here's a good example of there are 3 big cases where a function is going to fail to be differentiable. So like the absolute value function, the tangent of this part is positive 1, right? For all the points on this part. All the points on this part, the tangent is just itself negative 1. We have an abrupt change here, right? So we've got it's minus 1. Excuse me, the slope is positive 1, the slope is minus 1. And we have an abrupt change where that limit does not exist. For number 2, f's not continuous. So if it's not continuous, it has a break in it, it's not differentiable at a point. And if f prime is not defined at a point, then that means that it doesn't have a tangent line there. So these are the reasons why that limit fails to exist. The limit definition fails to exist. So the last thing mentioned in this section is the higher order derivatives. So since the derivative is a function itself, it has a derivative, possibly. Not necessarily everywhere, but it has a derivative. So you can take the derivative of the first derivative, and that's called the second derivative. And that is denoted with 2 apostrophes here. And then the Leibniz notation is d2y dx. People say dx squared. It's not really squared. This is just notation, meaning that you're taking the derivative twice of the original function. And then there's also a third derivative. We're just taking that one step farther. The third derivative is the derivative of the second derivative. You have 3 apostrophes and this notation. So, you're just applying the same concepts over again. The third derivative gives you the slopes of tangents of the second derivative. The second derivative gives you slopes of tangent to the first derivative. So the second derivative is going to be more interesting later on when we talk about graphs of functions in more detail and how you can determine what they're doing from the derivatives. So an example of the second and third derivative that you kind of might be able to relate to if you think back to the position function and velocity. So remember that the position function is just how far from some point an object is. And we said that its instantaneous rate of change is that first derivative, which gives us the velocity, which is the speed and direction of the moving object. And then the derivative of the velocity is acceleration. So that's giving us the change in the velocity of a function. So you can kind of relate to that when you accelerate in a car. And then the derivative of the acceleration is called jerk. So if you think of a sudden change in acceleration in a car, you know, and that jerking motion that occurs, that's the rate of change of the acceleration. And that's the third derivative. So in summary, what this section did was give us a new function derived from the original function, f prime of x. So it's just that difference quotient now with x instead of a. It's not at one particular point. It's generalized. The big takeaways are that when the derivative is positive, f is increasing. When the derivative is negative, f is decreasing. When the derivative is 0, f is changing direction or has a horizontal tangent. We looked at the different ways to, the different notations for derivative functions, where a derivative might not exist, where a function might not be differentiable, and also we talked about higher order derivatives.